Hi everyone, I'm Long Chen, and today I'm going to present our work, What Data Do We Need for Training an AV Motion Planner? This work would not have been possible without other co-authors and Leaf Level 5 team. So before we get started, please allow me to briefly introduce ourselves. We are from Level 5, Lyft's in-house self-driven department. We are building a self-driving system to increase access to safe and reliable transportation for people everywhere. So today, in this presentation, you will learn about why machine learning planner system is a promising way to self-driving, how we can collect more data, and the quality-quantity trade-offs, and the methodology for understanding what data we need. To begin with, let's see how traditional planning system works. At a very high level, the input data to the planner usually contains the map, the current ego pose, and the agent or obstacle poses. The traditional planning system, usually the rule-based planner, use handcrafted features such as the distance to agent, distance to limb boundaries, to evaluate all feasible trajectories and pick the one with lowest cost as the output trajectory. So the rule-based planner rely on human to define these features and tune the weights of each term. This method only works in limited conditions and is not scalable as L4 self-driven is a very complex problem with many edge cases. However, for machine learning planner, the handcrafted features are replaced with weights that can be learned during training to output the trajectory with maximum probability. The machine learning planner do not rely on human-defined features, so it has the capability to learn more complex tasks and edge cases if we give it enough data. So, how much data is enough? In last year, we published a motion prediction and planning dataset that contains 1,000 hours of driving data captured by our in-house self-driving vehicles. We show that the planner performance gets better and better with more and more data. However, even our dataset is the biggest one at the time we publish it, it's still far less than other tasks, such as for image detection. The ImageNet dataset has 14 million examples with annotation. So we need to get more data, but how do we collect them? The current way to collect data for training machine learning planner usually requires using the self-driving vehicles that contains all these expensive sensors to collect high-quality training data. But this method is not scalable, and this is the bottleneck that limiting the machine learning planner performance from continuous improvement. The solution is to leverage fleet learning. Imagine that if we can get training data from low-cost sensors attached to the consumer vehicles, the size of training data would be greatly boosted. After training the machine learning planner, we can deploy this planner to the actual self-driving vehicles and use the knowledge learned from the thousands and millions of human demonstrations for doing planning on the self-driving vehicles. In order to achieve this, the key question is what data do we need? There are always some trade-offs between quality and quantity. Clearly, with more expensive sensors like LiDAR, we are able to capture better quality data with longer range and accurate perception. While the low-cost cameras can be easily deployed on the consumer vehicles, we can only collect lower quality data with limited range and accuracy. And the most important thing is to find the balance between the quality and quantity, and collect data with the optimal sensor configuration. So to answer the question, what data do we need? The most naive way is to attach different sensors to the vehicles, collect lots of data, and run experiments to find out what sensor configuration is the best. However, This will be very expensive and time-consuming process. Well, in next slide, I will introduce our method to find out what data do we need. To find the optimal sensor configuration with simulated data. To achieve this, we leverage the existing self-driving vehicle data to simulate the lower quality data from low-cost sensors. After that, we train machine learning planner models using the simulated datasets and evaluate the performance using the test data from self-driving vehicles. This pipeline saves us lots of time and efforts to collect data with different sensors and also have the advantage of controlling the all-in variable to be the quality. Let's take a closer look at how we simulate lower quality data. We process the sensor data into mid-level representations that contains the semantic maps, the ego, and the agent poses, which can be easily manipulated and simulated. We use a quality alteration module to create simulated low-quality data by limiting the range and field of view, or changing the perception accuracy by adding random noises to the agent positions. After we simulated the lower quality data, we use a very simple imitation learning approach for training our machine learning planner. Our planner takes the middle-level driving logs as input and outputs the predicted trajectories. The differences between the predicted trajectories and ground truth trajectories will be used as a loss for training the network. Our implementation is open sourced and can be found out at planning.l5kit.org. In this slide, we show the performance of machine learning planner on different combinations of lower quality data we simulated. In this 3D bar chart, the x and y axis represent the different field of view and range, and the z-axis is the average displacement error of the different models. The lower, the better. We can see that the bar in the bottom with the lowest error is a model trained with AV quality data that has 360-degree field of view and range. By reducing the range and field of view, we can see that the model error will increase. One interesting finding is that the error increased dramatically after the field of view is smaller than 130 degrees, and the range is smaller than 40 meters. This suggests that the minimal sensor configuration should be more than 130-degree field of view and 40 meters range. But still, the better sensor will give better results. On the right side, we show the results for the accuracy alteration. The results suggest that the machine learning planner is not sensitive to the positional accuracy than rotational accuracy. However, the overall accuracy impact is very minimal compared to the range and field of view. With our experiment results, we understand better on what data do we need in order to train machine learning planner from low-cost sensors and deploy it on the self-driving vehicles. During our experimentations, another important finding is that we discovered that there are naturally some domain gaps between low-cost sensor data and high-quality data from self-driving vehicles. And training testing with different data from different distributions will likely decrease network performance. To remove the domain gaps, we introduced a domain adaptation module after we trained the models from simulated low-cost sensor data. Specifically, we fine-tuned the models with a small amount of data from self-driving vehicles, so the model adapts to the data distribution from high-quality data. And this method really works. Here we can see that the green bar shows by training with 100 hours of low-quality data and fine-tuned on a small amount of high-quality data, the error reduced dramatically compared to the blue and pink bars, which are the models using self-driving vehicle grade data and low-cost sensor data alone. When we give it more data, we can see that the performance of machine learning planner continue improving, and with the help of the domain adaptation, the greater amount of lower quality data beat a small amount of high quality data. This leads us to our conclusion. To summarize, we validated the hypothesis that lower quality data unlocks large dataset to train machine learning planner. We outlined a methodology for understanding the quality and quantity trade-off. We identified the domain adaptation is effective to bridge the gaps between the data from different sensors and makes it possible for learning machine learning planner from the fleet. That's all from us. Thank you so much for your attention. If you want to know about our results or code we use, you can go to our project website at planning.l5kit.org. If you're interested in solving the self-driving problem, please come and join us. Thank you.